So far, all of the motion in space we've talked about has already had the gravity component built in. Now we're going to talk about two-dimensional motion in a gravitational field, starting from the basic principles of Newton's second law. The motion of many objects that we're interested in, especially when gravity is present, can be modeled using Newton's second law, which basically says that the acceleration of an object that is in motion will be dependent on two things. The acceleration will depend on the sum of the forces acting on it, and it will depend on the mass of the object itself. I can write Newton's second law as the sum over I of the forces acting on the object, which is equal to the mass of the object times the acceleration vector with respect to the parameter t. If the sum of all the forces acting on the object is zero, then the acceleration will also be zero, and the object will either be at rest or moving along a straight line trajectory, and this is Newton's first law. The simplest problems that we can solve using Newton's second law are where the only force acting on the object happens to be the force due to gravity. The force due to gravity is always directed downwards, so in two dimensions we take this to be in the negative y direction. We use the letter little g to represent the acceleration due to gravity. This is approximately equal to 9.8 meters per second squared, or 32 feet per second squared, depending on the units we're working with. The force vector is equal to the mass of the object times the acceleration vector for the object as a function of the parameter t. I can write this as the mass times the acceleration vector is equal to the components 0 and negative mg when the only force acting on the object is the force due to gravity. This tells me that the acceleration due to gravity is negative g. In order to find the velocity, which has the components x prime of t, y prime of t, and the displacement or position, which has the components x of t, y of t, I will have to know two initial conditions. Typically, I want to know the velocity at t is equal to 0, and I'll use u sub 0 and v sub 0 as the components for this. And I want to know what my position is at t is equal to 0. I will use the components x sub 0 and y sub 0 for this. Once I have these two initial conditions and f is equal to m times the acceleration vector, I can solve for the velocity by simply integrating the acceleration vector. v of t is equal to the integral of a of t dt. This gives me negative the integral of g dt, so that my velocity vector is given by the components 0 and negative g times t plus the vector c, which is an arbitrary constant vector. Now I use the initial condition that the velocity vector at 0 is given by the components u0, v0, and I plug 0 in for t in my velocity equation in order to solve for the arbitrary constant c. I get the components u0, v0 equal to the 0 vector plus the vector c. I solve this for c, and I find that my vector c is equal to u0, v0. And my vector v of t is given by the components 0 and negative gt plus the vector u0, v0, and I add those components and I get v of t is equal to u0 and v0 minus gt. Once I have my velocity vector, I can solve for the position. Again, I just use integration. My position vector, r of t, is equal to the integral of the velocity vector, dt. I'm going to plug in my velocity vector that we just found, and I'm taking the integral of the components u0 and v0 minus gt dt. This gives me a position vector, r of t, which is equal to the components u0 t and v0 t minus 1/2 gt squared plus the arbitrary constant vector c. Once again, I use my initial condition, this time the initial condition for my position at t is equal to 0, and I use the components x sub 0, y sub 0. X sub 0, y sub 0 is equal to the 0, 0 vector plus the constant vector c. My arbitrary constant will therefore be given by the components x sub 0, y sub 0, and my position vector becomes the vector with components u naught t and v naught t minus 1/2 gt squared plus the components x naught and y naught. Putting this together, I get a vector with components u naught t plus x naught and negative 1/2 gt squared plus v naught t plus y naught. Now that I have my position, velocity, and acceleration vectors, I can use these as a foundation to expand what I can learn about motion equations and give us more specific information about an object's trajectory when only the force due to gravity is involved. First, we impose a coordinate system on the trajectory with a position at t equals 0 located at the origin. Then we consider an initial velocity, v of 0, which is given by the components u naught, v naught, which is also equal to the components of the magnitude of v naught times cosine theta and the magnitude of v naught times sine theta, where theta will be the angle between the horizontal and the velocity vector. If I plug these values into my position vector that we just developed, I get a position vector that can be used to find the information about the range, the time of flight, and the maximum height. My position vector now has the components the magnitude of v naught times cosine theta times t and negative 1/2 gt squared plus the magnitude of v naught sine of theta times t. If I take this vector, I can notice that the trajectory depends on the initial speed and the initial angle. Now, if I assume the object is launched from ground level at the origin over horizontal ground and that it returns to the ground when the second component of the position vector is 0, I can use this information to solve for time of flight. This means that I set the second component, negative 1/2 gt squared, plus the magnitude of v naught sine of theta times t equal to 0. I can factor t out, and I get two values that will make this statement true. T can equal 0, and this is my initial condition, or t can equal capital T, which is equal to 2 times the magnitude of v naught sine theta over g. This gives me my time of flight from the initial launch until it returns back to Earth. The range is this distance along the horizontal between the initial launch point and the point where the object returns to ground. This is the x-coordinate of the position vector, where little t is equal to capital T, the time of flight. So I plug capital T in to my x of t component function. I get the magnitude of v naught times cosine theta times 2 times the magnitude of v naught times sine theta over g. I simplify that product, and I get the range x of capital T is equal to the magnitude of v naught squared times the sine of 2 theta over g. The maximum height is the height above the ground where the object has a vertical velocity of 0. This means that we set y prime of t equal to 0 to get the time when the maximum height is reached. V of t is equal to the components given by the magnitude of v naught times cosine theta and minus gt plus the magnitude of v naught times sine of theta. If I set the y prime of t component equal to 0 and solve for little t, I'm able to find that little t is given by the magnitude of v naught times sine of theta over g, which is the time of flight capital T divided by 2. If I then plug half the time of flight into the y function itself, I get negative 1/2 times g times the quantity magnitude of v naught sine theta over g squared plus the magnitude of v naught times sine theta times the magnitude of v naught times sine theta over g. This simplifies to the magnitude of v naught squared times sine squared theta over 2g. This gives me the maximum height of the object after t is equal to 0. Now this works provided my object is going up and coming back. If I throw an object horizontally from a cliff and it drops down below the cliff level, my maximum height is obviously going to be the height at the top of the cliff. Use your common sense in analyzing the problem to understand when you can apply this and when you can't. Let's work an example. A golf ball has an initial position x naught y naught, which is equal to the 0 vector, when it is hit at an angle of 30 degrees with respect to the horizontal at an initial speed of 150 feet per second. I want to find the velocity and position vectors for all time t greater than or equal to 0, graph the trajectory, and determine the time of flight, range, and maximum height of the ball. First, I want to construct my position vector. My position vector r of t will have components with the form the magnitude of v naught times the cosine of theta times t, and negative 1/2 gt squared plus the magnitude of v naught times sine of theta times t. I know what my initial velocity is. It's 150 feet per second. That's my magnitude. I also know the angle at which the golf ball is launched. It's 30 degrees. So I plug those values in. My components become 150 times the cosine of 30 degrees times t, and negative 1/2 gt squared plus 150 times sine of 30 degrees times t. My position vector, once I do that, then I compute the numerical values, and my position vector becomes r of t is equal to the components 75 times the square root of 3 times t and negative 1/2 gt squared plus 75t. My velocity is the first derivative of my position, so I simply take the derivative of my position vector to find the velocity vector. This gives me a vector with the component 75 square root of 3 and negative 32t plus 75. Now I'm going to graph my trajectory. I set it up in a two-dimensional field with the x-axis being horizontal, the y-axis being vertical, and I plot my trajectory. This is a downward opening parabola with a maximum value at the vertex, which is slightly more than 300 feet from where the ball was originally launched. The maximum value on the graph looks to be approximately 88 feet. Now I want to find the time of flight. Capital T is equal to 2 times the magnitude of the initial velocity times the sine of theta over g. This means that I'm taking 2 times 150 feet per second times the sine of 30 degrees divided by 32 feet per second squared. I put the units in so that we can see that everything except the unit of seconds will cancel. This gives me a total time of flight of about 4.6875 seconds. My range is x of capital T. This has the form of the magnitude of the velocity squared times the sine of 2 theta divided by g, so that my range is given by 150 feet per second quantity squared times sine of 60 degrees, all divided by 32 feet per second squared. This gives me about 608.924 feet for the range along the horizontal. Finally, my maximum height is given by y of t over 2, which is given by the magnitude of v naught squared times sine squared of theta divided by 2g, so that my maximum height can be found by computing 150 feet per second squared times the sine of 30 squared over 64 feet per second squared, and that gives me about 87.89 feet for a maximum height. So now you get to try it. A baseball is thrown horizontally from a height of 10 feet above the ground with a speed of 132 feet per second. Pause the video and find the velocity and position vectors for all t greater than or equal to 0. Graph the trajectory and determine the time of flight and the range of the ball. The hint I give you here is that my formulas don't work. When you're ready, restart the video to check your understanding. So the first thing I need to do is come up with my position vector. R of t will be given by the components the magnitude of the initial velocity times the cosine of theta times t, and negative 1/2 gt squared plus the magnitude of the initial velocity times sine of theta times t plus y naught. This gives me components 132 times cosine of 0 times t and minus 16t squared plus 132 times sine of 0 times t plus 10. This simplifies to the components 132t and negative 16t squared plus 10. The velocity vector is the derivative of my position vector. V of t is given by the components 132 and negative 32t. When I graph my trajectory, notice that I start at 10 feet up from the origin along the vertical. This looks like the right half of a downward opening parabola that has the vertex centered at 0, 10, and it intersects the x-axis at about 104 feet. Now I need to find the time of flight and the range of the ball. I'm going to use the y component of my position vector and set it to 0 to find the time of flight, using -1/2 gt squared plus the magnitude of the initial velocity times the sine of theta times t plus y naught is equal to 0. My sine of theta is sine of 0, so that my middle term goes away, and I get -16 t squared plus 10 is equal to 0. This gives me t squared is equal to 5/8, and the total time of flight, capital T, is given by the square root of 5/8, which is approximately 0.79 seconds. My range of my baseball is x of capital T. This means I have 132 times the cosine of 0 times 0.79 seconds. That gives me a total range of 104.28 feet. This is how we work with two-dimensional motion when the only force that's acting on my object is the force due to gravity. Be sure and let me know if you have any questions.